High-temperature superconductivity at 100 K in lanthanum 3-X neodymium X nickel 2 oxide 7. Introduction and scientific context. Superconductivity, the flow of electricity with zero resistance, is one of modern physics' most transformative discoveries. Scientists have long sought materials that superconduct at higher temperatures, with the ultimate dream of room temperature operation. This paper marks a major step forward, reporting superconductivity approaching 100 Kelvin, about -173 degrees Celsius, in a nickelate compound, lanthanum 3-X neodymium X nickel 2 oxide 7. Nic-elates belong to a broader family of unconventional superconductors that includes the well-known cuprates, copper-based materials. They share layered crystal structures, making them ideal test beds for understanding how high-temperature superconductivity works. The specific compound studied here, lanthanum 3 nickel 2 oxide 7, is a Biele-Ruttleston-Popper phase, meaning it has two nickel oxygen layers sandwiched between spacer layers. However, this material does not superconduct at ordinary pressure. It requires extreme compression, on the order of tens of gigapascals, to reveal its superconducting nature. The challenge and the chemical substitution strategy. Synthesizing pure Biele or nic-elates has historically been difficult, and systematic studies have been hindered by phase impurities. The researchers overcame this by using chemical substitution. They replaced some of the lanthanum atoms with neodymium atoms, creating a series of lanthanum 3-X neodymium X nickel 2 oxide 7 compositions. Neodymium is slightly smaller than lanthanum, so this substitution acts as chemical pressure, shrinking the crystal lattice without needing external force. The team achieved record high substitution levels, up to 80% neodymium, opening new avenues for exploring structure-property relationships. Structural findings under pressure. Using X-ray diffraction, the researchers found that increasing neodymium content systematically compresses the lattice, particularly along the C-axis, the direction perpendicular to the nickel oxygen layers. This brings the layers closer together, which may enhance interlayer interactions crucial for superconductivity. They also observed that neodymium doping strengthens a magnetic ordering known as the spin density wave. Its transition temperature rises from about 138 Kelvin to 161 Kelvin, signaling stronger magnetic correlations. Under high pressure, these materials undergo a structural phase transition from a distorted orthorhombic form to a more symmetric tetragonal form. Crucially, this structural transition coincides with the emergence of superconductivity. For undoped lanthanum 3 nickel 2 oxide 7, the transition occurs at roughly 13 gigapascals, but for heavily doped lanthanum 0.9 neodymium 2.1 nickel 2 oxide 7, the transition pressure jumps to 26 gigapascals, more than double. This increase occurs because neodymium substitution stabilizes the distorted structure, raising the energy barrier to the high symmetry phase. Superconducting properties, pushing the temperature. The central achievement is the remarkable rise in the superconducting transition temperature. The researchers used two complementary techniques. First, they measured electrical resistance under high pressure. The onset of a resistance drop signals the superconducting transition. Undoped lanthanum 3 nickel 2 oxide 7 shows an onset near 82 Kelvin. With increasing neodymium, the onset climbs steadily, reaching 93 Kelvin in lanthanum 0.9 neodymium 2.1 nickel 2 oxide 7. By examining the derivative of resistance with temperature, they detected signatures of superconductivity at 96 to 97 Kelvin for the heavily doped compounds. Second, they employed radiofrequency transmission, a highly sensitive method that detects superconductivity by monitoring changes in magnetic response. This technique is especially useful for small, high-pressure samples where electrical contacts are difficult. The RF measurements revealed clear superconducting signatures at 100.5 Kelvin in lanthanum 0.9 neodymium 2.1 nickel 2 oxide 7, setting a new record for this family. Another composition, lanthanum 0.6 neodymium 2.4 nickel 2 oxide 7, showed a transition near 98 Kelvin. Magnetic field response. The researchers also measured how applied magnetic fields suppress superconductivity. The upper critical field, the maximum field the superconductor can withstand, was determined from resistance measurements under varying fields. For lanthanum 0.9 neodymium 2.1 nickel 2 oxide 7, the upper critical field at zero temperature is about 98.5 Tesla. For the X equals 2.4 compound, it is about 111 Tesla. These values are remarkably high, confirming the robustness of the superconducting state, even though they are slightly lower than the undoped material, which had a lower transition temperature. The temperature-pressure phase diagram. Combining structural and transport data, the authors constructed a phase diagram for lanthanum 3-X neodymium X nickel 2 oxide 7. It shows that the structural transition boundary shifts sharply upward with neodymium doping, and superconductivity appears only after this transition occurs. The maximum transition temperatures are achieved at pressures slightly above the structural transition, suggesting that modest additional compression beyond the symmetry change is beneficial. The diagram also reveals inhomogeneity. Different measurement techniques give slightly different onset temperatures, indicating that the sample contains regions with slightly varying compositions or local pressures, a common feature in high-pressure experiments. Correlating lattice structure with superconductivity. Perhaps the most insightful finding is a clear empirical correlation between the crystal lattice and the transition temperature. When the team plotted the maximum superconducting onset against the out-of-plane C-axis lattice constant for their materials and compared with data from other studies on bulk samples and thin films, a striking negative correlation emerged. Smaller C-axis parameters, meaning tighter interlayer spacing, consistently yield higher transition temperatures. This trend holds across different chemical substitutions and physical pressures. This result strongly suggests that interlayer coupling is a key driver of superconductivity. Compressing the layers enhances magnetic exchange interactions between them, which likely strengthens the pairing of electrons. In contrast, the in-plane lattice parameter shows a less direct correlation. It must fall within a narrow range for superconductivity to appear, but within that range, it does not strongly affect the maximum temperature. This distinction underscores that it is the coupling between layers, not just the two-dimensional planes themselves, that elevates the superconducting temperature. Implications and future directions. This work provides a powerful structural descriptor for designing higher temperature superconductors, reduce the interlayer spacing. Future efforts may explore even smaller rare earth substitutions, such as europium or gadolinium, to further compress the lattice. Additionally, the finding that compressively strained thin films can achieve similar transition temperatures as pressurized bulk samples suggests that strain engineering might one day eliminate the need for extreme external pressure, making these materials more practical. Conclusion. By systematically substituting neodymium into lanthanum 3 nickel 2 oxide 7, creating the lanthanum 3-X neodymium X nickel 2 oxide 7 series, the researchers have pushed the superconducting transition temperature to 100.5 Kelvin, a record for Bielier-Nick LATs. Their results reveal a direct link between lattice compression, enhanced magnetism, and higher superconductivity, with the interlayer spacing emerging as the critical parameter. While practical applications remain distant due to the high pressures required, these fundamental insights bring us closer to understanding the mysteries of high-temperature superconductivity and guide the search for even better materials.